We're now going to discuss frequency, amplitude, and wavelength. All right. This figure illustrates a method of producing a continuous wave or a steady stream of pulses on a very long string. One end of the string is connected to a blade that is set vibrating. As the blade oscillates vertically with simple harmonic motion, a traveling wave moving to the right is set up on the string. The figure shows the wave at intervals of 1/4 of a period. Note that each small segment of the string, such as P, oscillates vertically in the y direction with simple harmonic motion. That must be the case because each segment follows the simple harmonic motion of the blade. That means we can treat every segment of the string as a simple harmonic oscillator vibrating with the same frequency as the blade that drives the string. The horizontal dashed line represents the position of the string when no wave is present. The maximum distance the string moves above or below this equilibrium value is called the amplitude A of the wave. For the waves we will work with, the amplitude at the crest and the trough will be identical. Look at the top figure. The horizontal arrows show the distance between two successive points that behave identically. This distance is called the wavelength. Notice that it's from a peak to a peak. You could always use a trough to a trough. If you use a zero crossing, it has to be the zero crossing in the same direction. In other words, it's going from positive to negative on the zero. The wavelength is from the next positive to negative going zero crossing. You can't do, if you do a positive to negative zero crossing, the negative to the positive zero crossing is just a half wave. It's 1/2 lambda, and that's not sufficient. So you need a zero crossings in the same direction. All right, next slide. Come on, next slide. All right. Let's derive an expression for the speed of a wave. We start with the defining equation for the wave speed v. The wave speed is the speed at which a particular part of the wave, say a crest, moves through the medium. A wave advances a distance of one wavelength in a time interval equal to one period of the vibration. Taking delta x equals lambda and delta t equals t, we have our equation for wave speed. Because the frequency is the reciprocal of the period, we can write this as shown. Okay, so the velocity equals the wavelength divided by the period. Distance. If you remember from your grade school, you probably had a equation, distance equals rate times time. Well, if you think of distance as the lambda and velocity as the rate, then the velocity times the period will give you the wavelength. So it's really the same equation. It's just looks fancy because they use Greek letters like lambda. And that's it for this slide. That's just 39 and 40. Okay.